Hi and welcome to this online tutorial session. We're going to talk about IP version 4, okay, which is basically assigning IP addresses to different devices on a network and how they can all communicate with each other through IP. So the objective of this online session is to understand IP version 4. So essentially that's really dealing with the skill of working with IPv4. How are all these IP addresses assigned? How are the numbers given? What do they mean? When you mention an IP address, do you talk about IP version 4 or do you talk about IP version 6? Okay, which we'll discuss in a later session. But just to know what IP version 4 is, how the numbers are actually allocated and assigned to different devices on the network. So it's the skill of working with IPv4. In the ebook, if you want to start on page 68, this is where it's referenced in the ebook, lesson 4. Today's session doesn't completely map the ebook. I've tried to broke it down to make it a bit more simpler to understand, because the book has a lot of text trying to explain what all these numbers mean. So hopefully I've made it a little bit easier in this tutorial. And then if you look at Learn Key, which is under Course Essentials, session 3, and there also deals with this actual section, which is Understanding Protocols and Services, which is IPv4. Okay, so let's have a look. Here you can see we have a diagram here. It's just giving you a screen capture of IPv4, okay, which is 32 bits. And this is your IP address that most of you might be familiar or will have seen along the way often. And then because IP version 4 addresses are eventually going to run out, you're going to have IP version 6, which is 128 bytes in length, and it's assigned completely different looking compared to IPv4. But for the moment, IPv4 is still the majority IP that's used, or version 4 that is used in the local area networks today, and probably will be for the next 5 to 10 years. IP version 6 is available, but it hasn't completely taken over IPv4, so it's important to kind of concentrate maybe on that one for now. So that's what we're going to do. So IP stands for Internet Protocol, and then you have version 4, okay? So as a network administrator, you will use the Transmission Control Protocol, or /IP Internet Protocol. This is the most common protocol that is used, okay? You also have, it just says there that most technicians will refer to it just as IP, okay? It's just a short termination in the telecom terminology. So although the newer IPv6 has many advantages over its predecessors, which is IPv4, IPv4 is still the main majority of IP networks that are used in the lands today. Okay, so defining the TCP/IP model. So the IP resides on the network layer of the OSI model. The TCP/IP or TCP model is similar to the OSI model. It is often used by software manufacturers who are not as concerned with how much information is sent over physical media or how much data link is actually made. This model is composed of only 4 layers. So if you remember the OSI model, and I have a slide to show you, the OSI model has got 7 layers, whereas the TCP model has only got 4 layers. So it's mostly the software manufacturers would deal more so with this model, which is the TCP model, because I suppose software developers don't really care about the bottom 3 layers, which is your network data and physical layer. Not that they don't really care about it, but they wouldn't deal as much with it. Software developers would deal more so with the application layers and requests that are sent and received, rather than the actual hardware of the components. So programmers utilize the TCP/IP model more often than the OSI model. And as I said, they're more interested with the interfaces made on the transport layer and the application layer. So, network administrators usually benefit from the OSI model a lot more, because there is 7 layers in this model, and from the application layer all the way down to the physical layer, network administrators and engineers really need to understand what happens in each one of these layers. Okay, so it's like a life cycle of how data is sent from a request of a Google web page to actually going out, finding it and displaying it on the screen. So anything below the transport layer is taken care of by the TCP/IP stack within the operating system, which is set in stone. Programmers can utilize the TCP stack but cannot modify it. A networking person must be aware of the TCP model in case you need to interface with programmers or developers in the real world. So really what that means is network administrators really need to know the 7 layers and what happens in each of them. Whereas from, I guess, a programmer's point of view, they really only need to understand the TCP model and, I guess, the protocols that are involved within that actual stack or that model. They can't modify anything, whereas the engineers on the network layer, or the networking engineers, can actually modify things. Programmers are not interested in that. They just really want to know more so about the application set layer. Okay, so I've made reference there also on page 45 of your ebook. It gives you an example of the TCP model. So what I have here is I just have inserted a picture here where on the left hand side you can see the TCP/IP model. Okay, so you can see that it's got 4 layers. Okay, these 4 layers are your application layer, transport layer, network layer, and network interface layer. And then over on the right hand side you've got your OSI model, which is your application, presentation, session, transport network, data link, and physical layer. So these are the 7 layers of the OSI model. These are the 4 layers of the TCP/IP model. And then between each of these you can see the protocols and services that are actually involved in order to make all this communication happen. All this in the middle are actually called protocols and services, and this is how requests happen and how requests are understood in the networking world in order to literally be able to type in google.com on your computer. It goes out there to find the Google web page and display it on your screen. All that stuff that happens when you send that request all happens here within each of these models. But depending on which one you're focusing on, today's session we're looking at the one on the left hand side, which is your TCP/IP model. Okay. So let's see, you've got your protocol suite. So the Internet Protocol Suite has 4 layers. Okay, so the first one here in kind of the orangey red is your application layer. So this has, the application layer has network utilities like ping and trace route. Okay, so that's their requests that you can actually do here on the application layer. For example, you can ping an IP address, you can ping google.com just, you know, on the application layer to see if you've gotten a request back, to see if the web page is up and running, for example, and if it is, then obviously, you know, you can communicate. And for example, if you actually bring up your command line and you type in ping space www.google.com and you get a reply back, that means that the Google web page is actually up and running, so you can communicate with that, for example. Okay, the second layer you have is your transport layer, okay, which is here in purple, and you've got your TCP and your UDP protocols here on this layer. And what this does is it provides an end-to-end communication service. Okay, so we'll discuss more about that in detail as we go through this tutorial. The number 3, you've got your internet layer, which is here in blue. Okay, so this uses internetworking, which is a concept for connecting multiple networks with each other, with each other through gateways. So you have your IP, which again is going to be what we're going to be talking today about. Then you have your ICMP, your IGMP. Again, these are more protocols that are used in the internet layer, but we're really going to focus on today is TCP, and I will mention UDP here in the purple layer, and then, or the transport layer, and then you have in the blue section here, you've got your IP, which is on your internet layer. And then the last one we have is your link layer, and this is the physical and logical network components used to interconnect hosts and nodes on the network. So down here in the green, this is your actual physical connections. For example, your Ethernet cable, your DSL, which is coming in from your telephone line. These are actually the physicalness, the physical components on the network layer, and how they are actually connected physically and how they work logically. Whether, for example, you might have a star, a ring, a bus topology, depending on how the network is configured and set up. This all happens here in the green layer, which is your network layer. Okay, so next thing you have your IP protocol. So the protocol suite is multiple protocols all tied together called TCP/IP. Or you might often see reference DoD, which is Department of Defense model, or the Internet model. So there are three names, you could say: TCP/IP model, DoD, and Internet model. That is all referenced to when you talk about this actual protocol suite. So for example, the Department of Defense, what you can actually check that up on the internet anyway, but reference to that was made years and years ago when I guess the war was going on. If information needed to be sent across the network, what they used to do is they used to try and send packets, or this is how this whole concept originated from, was where they would try and send packets of information out there in the network, and they used to break it up. So you might have, say, a message of maybe 100 bytes of information that you want to send out, or 100 packets, sorry. So what that does is it'll actually individually send packet 1, 2, 3, all individually, and so on until all the 100 packets were actually delivered. So it was a way of, I guess, designing a model to stop people, I guess, interfering or intercepting with the information that was actually in those packets. So that's the reference of Department of Defense. So you can check that out anyway if you want to learn more about that. So the main protocol that we're going to talk about here is TCP and IP, and these main protocols work in two very different ways and very important ways to basically be able to send information out in the internet. So the first one we're going to talk about is IP. So IP is the main protocol within the TCP/IP model, and this protocol is used to control routing of different information to different computers, different devices, and different services on the network. So you've all heard of IP addresses. Well, the IP address deals with the IP address itself. It also deals with the subnet masks, the DNS, which is your domain name servers, and your default gateways. So IP deals with all of these actual IP addresses that are all assigned to each computer and each device on the network. IP protocol allows two computers to figure out where the other one is so that they can communicate. So basically what it really means is how computers can discover each other, how devices can discover each other in the network. They have IP addresses. Once you have an IP address on the network, you are basically discoverable. Okay, so let's talk about non-routable protocols. So there are routable protocols and there are also non-routable protocols. So with non-routable protocols, you have computers that once connected to the network can talk to each other and communicate. This can play havoc on the bandwidth utilization, as well as becoming very confusing and messy. So you can imagine if you have, I don't know, I only have 4 or 5, I have only 9 computers here, but say this was 99 computers and they're all connected individually to each other, and they're all sending messages out there. They don't really know where it's going. Well, they do, but it's, I guess, the way that it finds the sender, the way the sender finds the receiver, etc., can be quite confusing. It will use up a lot of bandwidth because of the way this configuration is set up, and because all of these are using non-routable protocols, it can become very messy. So if we talk about routable protocols, okay, so TCP/IP is a routable protocol. IP, IPX, these are all protocols that can be routable. And basically what that means is it allows you to divide big networks into smaller sub-networks. So being a routable protocol, you can connect to all the sub-networks using routers. Okay, so routable protocols, think of routers. So you can see here we've got 3 networks. So you've got network A, B, and network C. So network A has it's a multiple sub-network. Okay, so it's divided into smaller network. Then you have multiple sub-network B, and the same with C. And each of these have a router, okay, that's sitting on the edge of the network that connects to the internet. So being a routable protocol, you can connect all your sub-networks using routers. So the router here, okay, on each of these sub-networks A, B, and C, is how the information is going to be sent out to the internet. Request is going to come in through this router, and this router's intelligence is going to be able to distribute the message to the internet in order to get a request back. So for example, if we see down here multiple subnetwork C, so it's got an IP address, okay, so it wants to find google.com. So I'm here at my computer and I type in www.google.com and I press enter. So this request is going to check, the router here is going to check here inside my subnetwork C to say, okay, there's this web address, does this belong to anybody in my network? No, it doesn't. Okay, so the router sends this request out to the internet here, okay, this blue cloud, sends it out here and says, okay, I'm looking for this IP address. Do I go to router A or say router B? Okay, so router A sees this IP address and says, actually, hold on, I have a computer in my subnetwork that has this IP address, give me the request and pass it in here to my network. So the multiple subnetwork says, yes, this is on the server here for this web address. So let's send back the request back out from router A into the internet, down here to router C, and I get the request, and then google.com is displayed on my screen. So these routers have an individual IP address for each of them. Okay, so it's one IP address, and that's what the internet's looking at, is this IP address here assigned to my router. And past the router, within the internal LAN here, each single one of these computers have an individual IP address. So really all the internet deals with and cares about is the IP address of the router, and not the IP address of any computer or device within that LAN. Okay? So really, just to recap, what it does is a routable protocol allows you to divide very, very large networks into smaller subnetworks to make them more manageable in order to communicate. So the second one we're going to look at is your TCP protocol. Okay, so the last one was IP, now this is TCP/IP. So TCP is happening once the computers find each other. How are they going to talk? What language do they talk? How fast do they talk? And this is all done by the Transmission Control Protocol, which is your TCP. Okay. So with TCP, there is this terminology called windowing. And basically what windowing is the process of how data gets from one computer to another. So remember, with IP, it's how computers find each other. Okay, using their IP addresses, or how devices find each other. So whether it's a computer, whether it's your iPad or your notebook, whatever it might be, how computers find each other and discover each other in the network is done by IP, whereas TCP is actually how the data gets from one computer to another, and what language do they talk, how fast do they talk. Okay, so now we're talking about data. So the concept of windowing is that all data is sent from the client computer to the server computer and is broken down into packets. So for example, if you have a Word document or you have a movie, etc., whatever it might be that you want to actually send a request, so you have your client here and it sends a request and it wants to, I guess, send a Word document out onto the internet, or a movie. We'll pick a movie for example. So it wants to send this file out here, and then obviously the client and the server should communicate, which is what we're all familiar with. But what happens here in the middle, this request and this response, what actually happens here? This is called windowing. So the next slide will explain properly. So here we have the sender. Okay, so for example, what it's doing is it's sending packets of information out in the internet. So if it's a movie, and say the movie is maybe 1,000 packets at a time. Okay, so it's 1,000 packets it needs to send. So what it does is the sender sends packet 1, 2 and 3, and it's broken. The reason why packets or data is broken up into packets is to stop hackers, you know, or just, I guess, an easier way to send requests out to the internet is to actually stop people from interfering with the data that's trying to be sent. Okay, so for example, you have your sender here, and what it's doing is it's sending packet 1, 2 and 3, out to the receiver. So packet 1 goes, packet 2, packet 3 goes. So the receiver says, okay, I've gotten 1, 2 and 3. I'm going to send back an acknowledgement, okay, to say I've received packet 1, 2 and 3, send me packet 4. So then the sender says, okay, here's packet 4, 5 and 6. Then the receiver says, I've received 4, 5 and 6, now I want packet 7, and so on. So this is your TCP setup, where it sends a request and an acknowledgement is sent back to say, yes, send me more, or I've received the complete file, whatever it may be. So these are all done in stages. So the sender then might start sending, instead of sending 3 packets at a time, it might send 6 packets at a time, and keep sending the packets from the sender to the receiver, and eventually they might double and treble in the amount of packets that are sent, so that eventually the receiver will receive all of the packets. So the 1,000 packets will then be received. Once it's all received, you can actually watch the video. So just to recap, windowing is the sending of packets or sending of data in packets from the sender to receiver. The receiver sends back acknowledgements, and then the data is received. Okay. Now, so you also have components of the TCP IP device. So the components for a device on the network. Okay. So you're talking, and what the components need. So what I mean by components would be components for a device. So in order for a device to, I guess, be able to communicate and live in the network, it needs an IP address. It needs a subnet mask. It needs a default gateway. It needs a DNS server. And maybe on bigger networks then you might have a DHCP and you have a NAT, which I'll explain what all of those mean as I get to them. So that's what these devices need, and by the device I mean a computer, a PDA, your mobile phone that's requesting stuff on it, etc. That's your device, and your device on the network needs at least all of these 1 to 4, okay, in order to be able to communicate out there. So let's look at the first one. The first one is your IP address. So your IP addresses are used to signify a device or a component on the network. Every device on the network needs an IP address. So here's 3 examples of IP addresses. Okay, that's the first point. The second one we have is your subnet mask. So a way to segment a network logically so that different computers and different devices on the same physical network can talk to each other. So the practice of dividing a network into 2 or more networks is called subnetting. So for example, if we look at this picture here in the top right hand corner, not the networking fundamentals one, the one here with all the computers, we can see that all the computers are connected. They can all talk to each other, okay? And as I mentioned before, but very messy, a lot of bandwidth utilization is used up, etc. Okay, so what we really want to grasp here is how you can actually divide your network into sub-networks. So if you look at this circle here, well actually your ring, okay, so this would be a ring topology where all the computers are connected in a ring setup. Below that you've got your bus topology. Here you have a star topology and another star topology over here in the bottom left hand corner, and then up here again you have another bus. So these would be examples of maybe 5 different sub-networks within one network, and they are designed differently and probably operate logically in a different way. But the idea here is you're actually dividing your network into sub-networks. Okay, so all these circles here with the yellows, all right, you can imagine that these would be all routers that are connected together, and these routers all have a unique IP address to communicate, and then that individual router here has the intelligence then, once it receives an IP address from a request maybe coming in, to distribute it on its network and communicate and send the information to the receiver. So these routers, these 5 routers here, basically allow the request to come in, they're always listening for new data or new packets that are being transmitted, and the router knows, okay, I'm listening, there's a request coming in, that's not my IP address, send it on or disregard the request. So the listening router will always accept the IP address received if they have an internal IP address that's waiting to receive that piece of data. Okay, so the next one we're going to look at is your default gateway. So routers that connect to, so basically the default gateway are routers that connect to different subnetworks. So it allows computers to look at the LAN for the device it wants to communicate with or is looking for. Okay, so for this example I've mentioned Facebook. So if it's not within the LAN, then the default gateway then checks the internet to find the web page or the website, for example Facebook. And what it does is it creates a link between your device and the website you're trying to communicate with. Okay, so for example, we look at host B here. So you've got host A, B, and C are your internal LAN. That's your internal network. So host B wants to send a request out. So it types in www.facebook.com and presses enter. So it sends it out there into the network. So the gateway has intelligence to look inside and say this request is not inside my internal network. So I'm going to send it out to the internet to find facebook.com and reply with a response. So that's what the router does, is the router checks for the Facebook internally, and if it's not there, then the gateway will check the internet for Facebook. So that's what this default gateway is. That's the intelligence of it. In order to check internally for the request, if it's not here, the default gateway will then contact the internet to reply with a request for facebook.com. Okay. So the next one we have is your DNS server. So your DNS server is your domain name server. And what this is, it's a standard technology for managing the names of websites and other internet domains. So the DNS technology allows you to type in names onto your web browser, for example google.com, and your computer will automatically find the address on the internet. So to recap, what we have is I'm at my computer and I type in google.com. So I'm typing this into my browser, google.com. So the computer sees google.com, but the computer doesn't really understand what google.com is. Okay, so what it does is it has a DNS server in the network, and it says, I've got this request, google.com. Please check my DNS server and tell me what IP address google.com is equal to. So that's what this DNS server, it matches the domain name with an IP address. And when it does this mapping, then it returns the IP address to my computer, which is what my computer understands. It's IP addresses. It doesn't understand google.com. It just understands IP addresses. So then the computer then says, okay, I've received google.com is equal to this IP address. So now the computer is actually going to talk out to the internet to find google.com at this IP address 10.0.1.10, and it's going to reply with a response onto my screen, and then I will get google.com displayed on my screen. So that's what your DNS server does. It basically maps the domain name server, which is google.com, and makes it equal to an IP address so that the computer can understand it and then go look for that piece of information or that request that has come in. Okay, so that's your DNS server. Your next one is your DHCP, which is your Dynamic Host Control Protocol. And what this means is that every device on the network needs an IP address, and it cannot do anything without it. And if it doesn't have an IP address, then it can't communicate or talk with anything on the network because it's not discoverable. So to recap, every computer on the network needs an IP address, subnet mask, a default gateway, and a DNS server. So this DHCP, which is your Dynamic Host Control Protocol, what it does is it basically gives your computer information. How does it give your computer these IP addresses? What do these IP addresses, how are they actually distributed? So that's what this DHCP does. Okay, so it gives them out in a static form, or it gives them out in a dynamic form. So with the static form, what that means is you actually assign an IP address to a device, whether it's a computer, a desktop, a laptop, whatever it might be. It assigns an IP address that doesn't change. Or what can be given is a dynamic IP address, and dynamic means that it changes after a certain length of time. The IP address will change for each device. Okay, so maybe you only have it for 4 days, you might only have it for 10 days, whatever it might be. So it's dynamically changing. So let's have a closer look. So your static IP address, okay, static IP address is manually inputting the information for every device on the network. So that's what you do. You have an IP address for the device, your computer or your mobile phone. You have a subnet IP address. You have a default gateway IP address. And here you have 2 DNS servers. Okay, so remember the DNS server allows you to map the domain name with an IP address. So all these are configured by the system administrator, for example, and they're statically set up. So that means once you assign them, they're not going to change. So for example here, 2 computers on the same network within the same IP address may cause problems if they are given the same IP address. So you could imagine if you're doing it and you have, I don't know, maybe 25 computers in your network and you're all giving them the same IP, or you're all giving them IP addresses statically. Say for example, by mistake you might forget and give 2 computers the one IP address. Well, what happens there, for example, is if packets are sent to that computer that's got to 2 computers that have the same IP address, the packets are split. So say I've down here 1 million packets is equal to 1 video. So what that means is computer 1 will receive 500k of packets and computer 2 might receive 500k of packets. So no video is actually formed because these packets are divided because they're the same IP address. So to give you an example of, or to show you exactly where you would set up or give your device an IP address, okay, I'm going to show you. Sorry now. So let's go into control panel. Let's go network and internet. Network and shared center. So let's go in here to your LAN. Okay, so in here what I have is I'm connected here to the internet. Okay, so I can see my IP version 4 connectivity is to the internet. I'm enabled, I'm up and running. Click on details. This actually gives me all the details about my IP address here. So I have a physical address here. My DHCP is enabled. Okay, so what actually that means is that I'm actually assigned dynamic IP addresses. So that's my IP address here, 192.168.0.108, and my subnet is 255.255.255.0. My lease time, which I'll talk about in the next few slides, was given to me today at 9:30, and it's going to expire tomorrow at 9:30. So I've only got a 1-day lease time for this IP address, and what that means is after that time, either I would be renewed an IP address and it'll renew it, so I'll still keep the same IP address and keep it on for another day, or it might release my IP address and give me a new one. Okay, so this all comes down to the actual configuration of the network administrators and engineers. So then I have an IP version 4 default gateway IP address, and then I have a DHCP server IP address. I also have a DNS server IP address. And then you can actually see here, this is my IP version 6 IP address here, which we won't worry about that for this session. Okay, so that's the information from my network. But what I want to do is I want to actually statically assign an IP address. So if I click on properties and I select IP version 4 and I go properties, see the way it's set up is I obtain an IP address automatically. So that means it's dynamically changing, giving me an IP address randomly, depending on the lease time. So the chances are most of your setups or your networks will be like that. So I can actually statically set up an IP address. So if I type in here 192.168.5 and then 151. Oops, sorry. 51.1, and I press enter. I'm not going to do that now, because if I do, that means I'm generating a new IP address, and I will end up closing this session because my IP address will have discontinued, okay, or it'll be renewed. So I'm not going to do it, but I'm only giving you an example. It's actually in here where you will put your static IP information for your IP address, your subnet mask, your default gateway, and your DNS servers. But I'm going to go back to the way it was set up, which is obtain an IP address automatically and leave it be. So that's where you would do it and change it. Okay, so close all that. Okay, so that's your static IP address. Your dynamic IP address. So this is where the DHCP server comes into play. So what it does is it allows for automatic distribution of IP addresses, which is really important on big networks. So the DHCP server is called once a request happens. So for example, google.com search, and this will give out a random IP address, okay, but then it will also tell the computer or the device its gateway address and its subnet address. So that both of these, number 2 and 3, the gateway and the subnet, are all predefined by the network administrator. So the only thing that's changing all the time is the actual IP address. So this is all automatically done by the DHCP server, and it will keep record of the past IP addresses that are given out, so that it won't and cannot duplicate any addresses, which, as you can imagine, can cause a lot of confusion, and information is sent out there and basically lost if 2 devices have the same IP address. So it's a smarter configuration, smarter design, and it seems to be the preference in most networks is to use dynamic IP addresses. So what I've just shown you here is I just drew a diagram here where I'm showing you you've got 3 different devices here on your network, 3 different computers that all have individual IP addresses, and the DHCP server is here. Okay, so the system administrator configures the scope of the IP addresses. So up here I've just put in a scope of 192.168.1.100 all the way to 154. So that means it's got 154 IP addresses, so it goes from 101, 102 and so on. So that's my range or my scope of IP addresses, and each one of these fall within that. So I can have that many IP addresses here on all the computers that are connected, say, to the left hand side of the server. So the system administrator configures the scope, and they also configure the subnet, the gateway and the DNS IP addresses. So all really that the DHCP server deals with or needs to worry about, because all the rest is pre-configured or predefined, is the dynamic IP address for the device or computer. So you have a dynamic lease time, okay, and lease time is basically how long your computer is allowed to own the IP address given out. So the length of time, again, is configured by the system administrator. So whether it's 1 year, 6 months, 3 months, whatever it might be. Okay, so this is predefined and configured by the system administrator. So for this example, I'm going to say the lease time that my computer has this IP address is for 4 days. So usually at the 50% mark, okay, which is 2 days time, my computer will contact the server and say, I like my IP address, can I keep it? So what the DHCP server says is, okay, you can keep it for another 2 days. Or sorry, for another 4 days. Okay, so this is 8 days in total. And again, halfway through or 50% through that lease time, my computer is going to contact the server and say, okay, I still like it, can I keep it? And this continues. The same process happens over and over again. But in the example I showed you earlier, you can see that mine only had 1 day. So it's only basically 24 hours. So at 12 hours time, a request would go to the DHCP server to say, can I keep my IP address? And then after those 12 hours, then it'll go to 6 hours, then to 3, and so on. And if there is no response, then eventually the computer IP address will be renewed. So if it can't get a request or response, shall I say, from the DHCP server, then my IP address is renewed. It's released and renewed. I'm given a different IP address, and then possibly my previous IP address will be given to another device on the network. So that's your dynamic IP address. So just a note to make about the lease time. So the shorter the time, the DHCP lease time is, the more network traffic you have. Okay, but it means the less IP addressing are being used by the computers not on the network. The longer the lease time, the more IP addresses being used up, but the less time on the network. So really what it's saying there is, if you have a short lease time, then there's a lot of traffic generated, so it's only for one day. So say for argument's sake, in this building there might be 100 computers. Every one of them has a one day of lease time. Then you can imagine there's a lot of IP renewing or IP addresses being given out every day. Whereas if it was for a week, and say maybe only 70% of the computers are turned on, okay, for the 7 days, then that means that all the computers that are not turned on still have their IP address. So there's less IP addresses being used up. So it kind of depends which way the setup is, but it's just giving you an example of, depending which way your lease time works, whether you have a shorter lease time versus a longer lease time, you have more traffic or less traffic on the network. Okay, so now we're going to talk about NAT, which is your network address translation. So 10 to 15 years ago, every device on the, actually that should be in the world, in the network world, needed its own unique IP address. Okay, so what that meant is every computer, basically every device out there, all had IP addresses, okay, and they were uniquely given to each of those devices until NAT came along, which is your network address translation. So what is NAT? Need its own absolute unique IP address to itself. What it can do is it can reuse IP addresses within LANs, and when connected to the internet, all it needs is an external IP address to communicate with the internet. So what NAT does is it keeps from every device needing its own unique IP address. It utilizes the IP addresses internally by the router or the gateway, and it just uses one IP address from the gateway to talk to the internet. Okay, so let's have a look at some diagrams. Okay, so in this diagram here we can see, so this blue cloud here on the left hand side is your internet cloud. So what we have, we've got two routers, okay. The first router up here on the top, it's got an external IP address, okay, 208.55.44.1. So that's the IP address of this router. And then to the right hand side of the router, okay, which is your internal network, it's got an IP address range there, 192.168.1.2 all the way to 254. So all of these IP addresses here for these three devices are given as such. And then the second router that we have, again, has three devices out from it to the right hand side of the router, and these are actually also given the same IP address as the ones above. So what are we doing here? We're actually allocating the same IP addresses for router 1 up the top as it is for the router below internally, but the IP address of the router, or the external IP address here, is different. So when the router tries to communicate with the internet, all it sees is these addresses here in orange, 208.55.44.1 and 209.77.68.44. That's all it sees. It doesn't care about anything to the right of that, which is in your internal LAN. It doesn't care about that. All it cares about is the IP address of the external device here, which is the router. And the intelligence is built within the router. Okay, so its NAT is built into the intelligence of this router in order to send and receive information in and out of the network, but at the same time allowing IP addresses to be reused within different subnetworks. Okay, so these are both two subnetworks here. So what do all these numbers mean? All these IP addresses that we see, what do they mean? Okay, so I'm going to try and make this as simple as I can, because it can become quite confusing, and I know the book I don't really think it explains it quite well. So hopefully my drawings here and these few screenshots will help me explain it a little bit better. So an IP address has 4 octets, okay? So you have 10, 1, 10, 1. So 10.1.10.1. So what do these mean? So each one of these here is 4 octets. So you've got 8 bits here, 8 bits here, 8 bits here, and 8 bits here. So one of the 8 bits is equal to an octet. So you've got 1, 2, 3, 4, 4 octets here in an IP address. So one single octet, which is all ones, is equal to 8 bits. If you have them all zeros, okay, it's still equal to 8 bits, but it just means either it's on or it's off. So obviously 1 means it's on and 2 means it's off. So you're like saying, what does that mean? What does on and off mean? Okay, so I'm going to explain it in the next slide. So just to recap, you have an IP address here. You've got 8 bits. Okay, so you've got 1, 2, 3, 4, 5, 6, 7, 8. So you've got 8 bits here where this 1 is, okay, which is equal to 1 octet. And then your octets are either ones or zeros, and ones means it's on or 0 means it's off. Okay, so let's go a little bit deeper. Okay, so if you add up all the numbers, okay, for one IP address, so you said this IP address here, okay, is 8 bits, and all of these add up to a number. So the first one to the far right hand side is 1, the next one is 2, the next one is 4, and what it does is it doubles in numbers as it moves along. So 1, 2, 4, 8, 16, 32, 64, and 128. So all of those added up together within this 1 octet is equal to 255 if you add all those numbers up together. So how do we get these zeros and ones? So here I'm just going to open up a tool to allow me to draw, and I'll see if this will explain a little bit easier. Okay. So let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so all of these is equal to 2, 5, 5. So let's see. Say if we turn, so say I'm going to say this one's going to be equal to 1, 2, 4, 8, 16, 32, 64, 128. So what I'm going to do is, say I want an IP address of 1, so 1, 0, 0, 0, 1, 1, 1, 0. So you've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so obviously this is that, this is equal to that, and so on. This is equal to 1. Okay. So where I have a 1 here, okay, what I want to do is I want to draw a 1 up here. So let's go see. So you've got a 1 here, a 1 here, and a 1 here. So you've got 128, 8, 4, and 2. Okay, so I know I seem a bit simple writing these out, but anyway, I'll just do it to make it as clear as I can. 16, 17, 18, 19, 21, 22. Okay, and then we have 4 and 1. Okay, so what that means is that becomes an IP address of 142. So we're only working with the very last octet, which is on the right hand side. So obviously this octet means, or this one has an IP address that you need to configure, this one, and then the last part there is 142. So let me recap. All of these numbers here added together equals 255. So what I want to do is I want to be able to, I can actually draw in zeros there. I want to be able to assign an IP address. So my system administrator says to me, okay, I want you to give this computer an IP address of, let's, for argument's sake, let's just call it 168.10 and then 3 and then .142. So I need to figure out, what does 142 mean? If I break it down, how do I actually come up with this number of 142? So this is how I do it. You've got 1, 2, 4, they all double up in size as they increase. And I have 142, so I need to find that number here, add them all up to make sure I have this number. So I've got 128 plus 8 plus 4 plus 2, which is equal to 142. So that gives me that bit of my IP address. Okay, so let's go back to the presentation. So hopefully that might have helped explain it a little bit easier. Okay, so looking at these IP addresses here, okay, so if I look at this one here, so I have IP address 192.168.6.128. So all I've done is I've given this one here an IP address of 1. So that equals to 128. So that's where I get this figure, this figure here from. Okay, so again, I have this one here, 129. So we know this one equals to 128, and then you just use 129. That gives me the IP address here, just for this part. So you can obviously individually do it for, so I could say 129 on this one. We could say this is 6, this adds up to 168, and this adds up to 192. Okay, so that's all for this one here. So that's what these numbers mean. That's how you can configure IP addresses, and if you need to break them down to find out where do you even come up with these numbers here, how are they set up. Okay, so just in summary, you've got your 4 octets, okay, so octet 1, 2, 3, 4. Then you have either on or off. So by on, that means there's a 1 beside them. If it's off, it means it's a 0. And then if you add up all the numbers together, you come up with the number of 255, okay, which is that is the max, okay, so that is your max amount of numbers that you can have allocated to 1 octet, which is an IP address. Well, sorry, not it is an IP address, it's part of an IP address. You need 4 of these octets to be equal to 1 IP address. Okay, so I hope that makes it a little bit easier. Okay, so that's basically your numbering. So what we want to do is, let's just recap, okay? So in order for an octet, in order for an IP address to function on the internet, there must be a properly configured IP address, okay? There must be a compatible subnet mask, which again is usually assigned by your system administrator. To connect to the internet, you also need a default gateway and you need a DNS server. And remember, your default gateway has the intelligence to look for the different IP addresses within your LAN in order to route whichever way the packet is to be sent. Your DNS server basically maps your DNS server, which is equal to an IP address. And then you have your advanced examples of your IP configuration can include subnetting, and it can also include NAT.